Hello and welcome to your Algebra 2 lesson 12.3 and 12.4. Our objective for today is to analyze geometric sequences and series, including infinite geometric series. So what is a geometric sequence? We learned that an arithmetic sequence has a constant difference, a common difference, the number you add to get from one term to the next. For a geometric sequence, we're going to have a sequence for which the ratio of any term to the previous term, so like A2 divided by A1, A3 divided by A2, and so on, is constant. Now, another way of thinking about this is that one multiplies by a constant value to get from one term to the next. So you multiply the first term by 2 to get the second term, and then the second term times 2 to get the third term. Or it could be a fraction. You multiply the first term times a half, and then the second term times a half, and then the third term times a half to get to the next term. This constant value is called the constant ratio and is denoted by R. So the first thing we're going to do is we're going to identify whether or not we have geometric sequences. So here we've got one, 4, 10, 18, 28, 40. So I can't tell really quickly looking at it what I would multiply 4 by to give me 10. So I'm going to actually look at the ratio of A2 divided by A1. That gives me 10 divided by 4, which is 5 halves. Then I'm going to look and see if we get the same thing when we do A3 divided by A2. But there we get 18 divided by 10, which reduces to 9/5. Those are two different numbers. So really that's enough to tell you that the sequence is not geometric, because you multiply by 5 halves to go from 4 to 10, but you multiply by 9/5 to go from 10 to 18. So we're not multiplying by a constant value. If you want to check some more, you can, but you certainly don't have to. So the ratios are different, so the sequence is not geometric. Let's look at this next one before I show you the way the book suggests you do it. We've got 6, 25, 1, 25, 25, 5, 1. So when I look at this, I go, well, it looks like over here 5 divided by 5 is 1, 25 divided by 5 is 5. Yep, 125 divided by 5 is 25, 625 divided by 5 is 125. So we're dividing to get from one term to the next, but dividing by a number is the same thing as multiplying by its reciprocal. So I could think of this as multiplying by 1/5 to get from one term to the next. And that works. So this is geometric with R equaling 1/5, because that's what I get, or that's what I need to multiply one term by to get to the next term. We can also work it by looking at the ratio of each term to the prior term. So A2 divided by A1 is 125 over 625, which is 1/5. A3 divided by A2, that's 25 over 125, which reduces to 1/5. A4 over A3, it's 5 over 25, which is 1/5. And A5 divided by A4 is 1/5. So yes, it is geometric, and R is 1/5. Okay, so we need an nth term formula for geometric sequence, just like we had for arithmetic sequence. The nth term of a geometric sequence with the first term A1 and common ratio R is given by the nth term equals the first term times R to the n minus 1. So for example, the nth term of a geometric sequence with the first term of 3 and a common ratio of 2 is given by the nth term equals 3 times 2 to the n minus 1. Notice that the 2 is raised to the n minus 1 power first and then multiplied by 3. We never forget our order of operations here. In other words, never do 6 to the n minus 1, because that is not equal to 3 times 2 to the n minus 1. All right, so we're going to write the rule for the nth term of the sequence and then find A7. So our first sequence here, we've got 4, 20, 100, 500. So the first term here is 4. We can see that. And you can either find R by doing A2 divided by A1, or you can just look at this and go, okay, what do I multiply 4 by to give me 20? Well, I'll multiply by 5. Does that continue to work? 5 times 20 is 100. 5 times 100 is 500, so that definitely works. So R is 5. So in general, the nth term is equal to the first term times R to the n minus 1. So we're going to plug in 4 for A1 and 5 for R, and we get that the nth term equals 4 times 5 to the n minus 1 power. So to find the 7th term, that is A7, so we're going to plug in 7 for n. We're going to have 4 times 5 to the 7 minus 1, which then we simplify, gives us 62,500. All right, so we're looking at this second sequence here where we go 152 to negative 76 to 38 to negative 19. Whenever the signs go back and forth like that, that is a hint that R is negative. The sequence is geometric with the first term equaling 152, right? Yep, there's the first term, 152. To figure out what R is, we do second term divided by first term. So negative 76 divided by 152, which is negative 1/2. So a rule for the nth term is, and we'll plug in 152 for A1 and negative 1/2 for R. So we get 152 times negative 1/2 to the n minus 1 power. If we find the seventh term, we're going to plug in 7 for n, and so we're going to have 152 times negative 1/2 to the 7 minus 1 power, so to the 6th power, and that simplifies to give us 19/8. All right, so for example 3, it says one term of a geometric sequence is A4 is 12, so the fourth term equals 12, and the common ratio is 2. We want to write out the rule for the nth term. So let's see. We're going to use the general rule to find the first term. So the general rule again is AN equals A1 times R to the n minus 1. We're going to substitute 4 for n. So the fourth term is going to equal A1 times R to the 4 minus 1. We're going to plug in everything else we know. We know that A4 actually equals 12, and we know R is 2. 4 minus 1 is 3, so we have 12 equals the first term times 2 to the 3rd power. 2 to the 3rd power is 8. 12 divided by 8 is 1.5, so 1.5 equals the first term. Now we want to write the nth term formula. So the general rule is the nth term equals the first term times R to the n minus 1. We're going to plug in 1.5 for the first term and 2 for R, and we're going to have 1.5 times 2 to the n minus 1. All right, example 4. Two terms of a geometric sequence are A3 equals 248, so the third term is 248, and A6 equals 3072. So the sixth term is 3072. We're going to find a rule for the nth term. All right, we're going to write a system of equations using AN equals, a little typo there, let me fix that. AN equals A1 times R to the n minus 1. Substituting 3 for n and then 6 for n in equation 2. So we're going to have two equations, one for each case that they gave us. They gave us a case for the third term and a case for the sixth term. So we know A3 equals A1 times R to the 3 minus 1, which we know A3 equals to negative 48. That wasn't supposed to be a 248. Oh my goodness. I hate it when they do that. But sometimes they will have a 2 where they mean to have a negative. So I apologize for that. So we're going to have negative 48 equals A1 times R squared, because 3 minus 1 is 2. And then our next equation we're going to get from what we know about the sixth term. So A6 equals A1 times R to the 6 minus 1. Well, the sixth term equals 3072. And that's going to be A1 times R to the 5th, because 6 minus 1 is R to the 5th. All right, so we're going to solve the system. First thing we're going to do is we're going to solve equation 1 for A1. So let's look back here. We have negative 48 equals A1 times R squared. So to solve for A1, we divide both sides by R squared. So negative 48 divided by R squared is equal to the first term. It's equal to A1. Now we're going to substitute it in to the other equation, into equation 2. So we're going to have 3072 equals, and instead of A1, we're substituting in negative 48 over R squared times R to the 5th. Now, we have R to the 5th on top, because if we multiply this, if you wanted to put R to the 5th over 1, you could. You're going to have negative 48 times R to the 5th over R squared. That means we're going to cancel out 2 factors of R from these 5 factors of R. And we're going to have 3072 equals negative 48 times r cubed. So we're trying to solve for r. So we're going to divide both sides by negative 48. And then and that'll give us negative 64. And then we take the cube root of both sides, which will give us negative 4 equals r. Now we can take r, and you can either substitute it in right here or in the first equation, just in general, and solve for a1. So negative 48 equals a1 times negative 4 squared. Negative 4 squared, remember, it's negative 4 times negative 4 is 16. If we do negative 48 divided by 16, we get negative 3. So a1 is equal to negative 3. So our general rule, an equals a1 times r to the n minus 1, is going to give us an equals negative 3 times negative 4 to the n minus 1, substituting in negative 3 for a1 and negative 4 for r. All right, the sum of a finite geometric series, so the first 5 terms, or the first 10 terms, is going to be given with Sn equals a1 times 1 minus r to the n over 1 minus r. Now we do have to make sure that the common ratio is not equal to 1, because this formula will not work. And the reason it will not work is because if you substitute in 1 for r, you'll have 1 minus 1 in the denominator, which gives you 0. All right. So we're going to find the sum of the geometric series, and we've got summation notation. We've got I equals 1 to 16 of 4 times 3 to the I minus 1. So we need to identify the first term. So A1 is equal to 4 times 3 to 1 minus 1 power. 1 minus 1 is 0. 3 to the 0 power is 1 times 4 is 4. We're going to identify the common ratio. That is the number here that is raised to the power. And so it's 3. And now we're going to write the rule for S16, the sum of the first 16 terms, because that's what we're told that we want. We want I equals 1 to 16, so we want the sum of the first 16 terms. It's going to equal the first term times 1 minus r to the 16th power over 1 minus r. So let's substitute in 4 for a1 and 3 for r. And we're going to have 4 times 1 minus 3 to the 16th over 1 minus 3. We'll evaluate that with our handy-dandy calculators. And we get 86,093,440. All right. Now, here's the cool thing. Remember, with arithmetic series, we're talking about adding, we can find the sums of finite series only. There are cases of geometric series where we can find the infinite sum, which is really cool. It works provided that the common ratio has an absolute value less than 1. If the common ratio has an absolute value greater than or equal to 1, the infinite series has no sum, because each new term adds too much value. When the absolute value of r is less than 1, each additional term just completes the total. Just gets it closer and closer to the total it's approaching. And it's real easy to work with. It's just a1 over 1 minus r. All right, we're going to find the sum of the infinite series given below. We've got I equals 1 to infinity of 5 times 0.8 to the I minus 1 power. So we want to identify a1, and then we want to look at r. So a1, if you plug in 1, you're going to have 1 minus 1 there, which gives you the 0 power, which 0.8 to the 0 power is just 1, times 5 is 5. This little number that's outside the parentheses that's not being raised to the power, that is equal to a1. The number that's raised to a power is r. And so your infinite sum is going to equal to 5 over 1 minus 0.8, and that gives you 25. I do want to point out you need to check that the absolute value of r is less than 1. All right, if we look at the next series, you have a1 equaling 1 and r equaling negative 3/4. Negative 3/4 has an absolute value less than 1, so we're going to plug in. We have 1 over 1 minus negative 3/4, so that's 1 plus 3/4. And so that 1 is 4 over 4 plus 3 over 4 gives you 7/4. 1 divided by 7/4 is 4/7. All right, for example 7, what is the sum of the infinite series 1, -3, 9, -27, plus on and on and on? First thing you do, you identify A1 is 1, and A2 is -3, so R is equal to -3 divided by 1. It's -3. The problem is the absolute value of R is greater than or equal to 1, so the sum does not exist. Okay, the infinite sum just doesn't happen. So the correct answer is D. Okay, guys, that's it for this video. Make sure you can do the problems to try on your own. If you can't, review the video and try again, or come in and see me because you want to be able to hit the ground running when you get to class. I will see you soon. Have a good day.